don't worry about fitting your talk in. So yeah, next up is Cade.
Sure, thank you. So we're here to talk about towards cumulative semantics. So the crux of our research is trying to preserve time. So lost work is lost time. And without reuse, every analysis that you build is kind of like a tool that only has one function. So as a result, it often gets left behind, and you lose the time you spent implementing it. So in this sense, like a screwdriver with one head is kind of like a monolithic interpreter. So every time you write an evaluation, if you have one interpreter for that evaluation that's not generic, you lose all the time as you move on to new functions. So in this sense, we're going to walk through a simple expression language. So we have expressions that are either constant numbers, an addition of two expressions, or an if. And here we have if not zero, because we're just dealing with numbers. So our evaluation expression takes in an e and is pinned to int, so it's non-generic. And then we match against the type of expression we have. So for constants, we just return back a constant. For expressions, we evaluate each side of addition, or it's not updating on there. I'm not sure if there's something going on. So yeah, for addition, we evaluate both expressions. So we can see here that evaluation order is pinned. So we have to evaluate the first one, then we have to evaluate the second one. And then for if, we have to either evaluate the true condition or the false. So false is marked by 0 here, and then any other number will give us true. So what if we could build a library of abstract semantics, which would give us a tool that we could reuse depending on the abstract domain that we're operating in? So in this sense, kind of like a drill head would be a generic evaluation function, and then each of these different bits that we can put in are kind of like abstract domains. So in this sense, we have a generic function that can take different domains, allowing us to focus on building new domains instead of building new evaluations. And the terminology we use for this is substantiated. So we say that you substantiate your evaluation with semantics, being an abstract domain. And this is pretty commonplace. So the way that we see this is usually with type classes or with modules. So now evaluation takes in some generic A and returns it. And instead of having pinned semantics for each operation, we have this interface that we adhere to. However, you can see here that usually the evaluation order is still fixed. So that's the second axis of the problem that we tackle. So firstly, an abstract domain is not an abstract semantics. A domain is simply parameterized by the values it can contain and the operations that produce them, but it has nothing to do with control flow. So here we can see that we need to take our expression to either integers, which would be our concrete domain, the interval domain, or something like the symbolic domain. And these introduce domain values, and we implement this via algebraic effects. And the second axis of our problem is control flow modulation. So an abstract semantics is an abstract domain plus the control flow for that specific semantics. So for instance, in the concrete domain, if we encounter an if statement, we can either go through the true branch or the false branch, but we can't go through both. However, for something like the interval domain, we don't always know if we're in the true branch or the false branch, so we have to be able to evaluate both sides and then join their results. So our goal is to have something like a series of components that can be mixed and matched to substantiate some generic evaluation function. So for instance, if we pair branch and control flow with the integer domain semantics, we get a substantiated evaluation function. And for us, this would be the concrete semantics of our little language. However, if we decide to pair non-branching control flow with the interval domain semantics, we get a substantiated abstract evaluation for this little language. So our main contributions are using algebraic effects to implement introduction handlers, elimination handlers, and then combine both of them to get what we call cumulative abstract semantics, because you can accumulate these components without rewriting or revising your evaluation function. So the first step is this domain value parametricity. So here, instead of using type classes, we leverage effects. So for plus, we can see we have some generic domain D, and we know that we get two values in this domain and then produce a value in this domain. So a handler for this effect for integers would look like simple addition in your meta language, where we have the plus operator. And for intervals, we can give it new semantics, where we take the low and high values, add them, and then get a new interval. And we call these introduction handlers because they simply introduce domain-specific values. So for instance here, instead of passing E1 and E2 to this plus and evaluating both sides, we pass the evaluation to this plus I, or plus introduction handler. However, we can see that the evaluation order is still fixed. We still have eval E1 and then eval E2. So now we bring up elimination handlers, which allow us to separate control flow from the abstract domain. So here we can see that for our if not zero example, instead of having to evaluate the guard, the true and the false, inside whatever structure we're using to abstract the domain, we have the evaluation on the outside, which means that our effect is able to determine control flow and the order of control flow. So here we have a branching handler for our if elimination effect. We can see that we use these K's, which are continuations in an effect handler, to evaluate the guard value, and then to use that guard value to match against 0 or false. But this throws away one value. So we get our A out, our generic A. But if we want something that evaluates each branch of the if expression, we can use multiple continuations to evaluate the guard, the true branch, and the false branch. And the last step here missing is we need to decide how to join these values to get into our abstract domain A. So these elimination handlers eliminate syntax and modulate control flow. And the main crux of this is that they move the evaluation from inside the device you use to create semantic domains to the outside. So we don't know anything about the order of evaluation in our generic function. And we can see that we pair this with an introduction handler. So the introduction handler determines how values are produced or joined, whereas the elimination handler determines the order of control flow. So one thing that we have to note is values are sometimes joined inside an analysis. So if we have a simple branching control flow, we know there's no joining. We take either the true value or the false value. However, if we want to do non-branching, we evaluate all branches and then pass it to our introduction handler. And here we can have special operations like join. So for the interval domain, we need to join the result of going through true and false instead of throwing one away. And by doing this, we create these little components that we can accumulate, hence the name cumulative abstract semantics. And just to give a final demo through this, we can see if we hit the if guard and we're in the concrete domain, we go through either the true or the false branch. However, if we need to join the result of both the true and false branch, we can swap out the handler for the if elimination. And we can now go through both the true and false branch and then get a value in our domain. And that's everything. Once we get through there, we have this idea of cumulative abstract semantics, and we're currently experimenting with building a large subset of Python and trying to create different abstract semantics for it.
Yeah. Catching up on time here, so time for questions. Yeah.
I have a small question. Thank you for the interesting work. I was trying to compare this work with the abstract and definitional interpreter framework, where you write a definitional monadic interpreter and then like swap in different monads to to interpret like different abstractions, right? So like, how does this compare to that work?
Gotcha. So when we were starting this, initially we were thinking about using a monadic approach, but the issue with that are some of the same issues we saw in earlier talks. We have to deal with transformers and you have to lift. So the main idea here is that the handlers can kind of be stacked on top of each other, so to speak. So your evaluation function remains generic and you don't have to know anything about the types or transforms in that function. And then you can swap or surround it with different handlers for different semantics.
Isn't that like kind of the approach done in the abstract and definition interpreters? Because like you have a generic definitional interpreter and then you swap in different monads, as in you swap in different handlers, right?
Yeah.
So like.
I guess the main difference there is that when you're using monads, even when you're swapping them out, you still have this notion of a monad stack that you have to lift through. So with the algebraic effect handlers, you kind of lose that added complexity and you gain the ability to simply have a handling function. And then by swapping those handling functions, you don't have to worry about the plumbing, so to speak. So it makes it a little bit simpler to compose.
Yeah, got it. Thank you.
Thank you for very interesting talk. Oh. Okay. Do you know the word tagless final?
Tagless.
Invented by Oleg Serov and others.
Yeah.
Tagless final. So your application will look like tagless, that exactly, almost exactly the same as tagless, what tagless final offers. Now, of course, well, you did some systematic approach, but can you compare your approach with tagless final?
I looked through that really early on, but I'm not super familiar with it, so I don't think I can compare it very well right now.
We have a program that we can, well, define a lot of different interpretations of the same source program. So.
Gotcha. I think the main difference, or at least because I don't remember it super specifically, the advantage that we got with the effects was having multiple continuations, because then we can kind of swap out the order. So in some of the testing, we made some handlers that ran backwards, and we were able to get all the way up to a backwards symbolic evaluation for a really simple language. I'll have to look at that again, but the main thing for us was just kind of having this component that could go forwards, backwards, or non-branching.
There are certainly close connections between tagless representations and handlers, so it's not surprising that you're seeing that. Question here.
Thanks for a nice talk. Do you think you could get rid of the elimination handlers if you made eval and handleable effect, so you could call it at the appropriate times in your introduction handlers?
So I am not sure about that approach. Right now what we're doing is we have two implementations, one with continuation passing, and then one using algebraic effects. So the main idea here that doesn't shine through perfectly with if is when you have sequencing. The elimination effect is really good because you can swap which way you sequence for forwards and backwards. And with the algebraic effects in languages that have them first class, some of them do stack swapping, so you get really high performance using those continuations. So we haven't looked into that yet, but I think that's similar to the CPS style that we're doing right now.
Okay, thanks.
Is that a question here? Yeah.
Thanks. Oh, sorry, I'm a bit unfamiliar with this, so apologies if this is a silly question. I was just wondering, in the handler for ifs, in the abstract domain, don't you get like a combinatorial explosion if you call the continuation, like on every branch?
So you can get that in certain languages. So one thing that we faced when we started, we were using Coca, is that when you have multiple continuations with with multiple effect types, so here these are different effect types, you have dynamic algebraic effects, meaning it reaches for the closest handler, they're not lexically scoped. So what can happen is the continuations don't capture everything they should. So in a while loop, state wasn't being registered as changing, so we were getting infinite iteration and non-termination. But one way we got around this is if you have one effect type, the scope of each of the sub-effects is known at runtime. So this was able to handle that and kind of correct that issue for us.
Thanks.
Okay, thanks.